Silicones are mostly known for what they don't do. They don't dissolve in water, they don't degrade at high temperature or under high voltage, and we thought that that set of properties could be interesting if modified with some organic chemistry. If you take this commercial vinyl silicone and add first alkoxy groups using hydrosilylation and then vinyl groups using the Pierce-Rubinstein reaction, one can convert one vinyl group into three to make this multifunctional material. Still not soluble in water or with aqueous reagents. However, a thiol-ene reaction between SH, which adds to the carbon-carbon double bond under radical conditions, allows one to readily prepare these materials that have three sulfides near the end and either three amines or three carboxylic acids at the actual end of the silicone polymers, depending on whether you use cysteamine or thiopropiionic acid. Now we've incorporated a lot of functionality, and we like the idea that these sulfur ligands will be soft, whereas the amine and particularly carboxylic acid ligands will be hard, such that in the presence of a metal, this cluster of functional groups should be able to do a hexadentate or tridentate coordination. Well, if you expose metals, multivalent metals, to these materials, what you find is under certain circumstances, you could get cross-linking as shown here, where the metal is bridging more than one of these silicones. Otherwise, what happens is it's extremely easy to extract metals like copper or iron or palladium out of aqueous solutions because of this functionality that acts at the interface to drag these heavy metals out of water into the silicone phase. And that might be interesting in its own right as a way of functionalizing the silicone to remove heavy metals, but we think it also is interesting because that functionality could be used in other ways. This is appearing in an open access paper in Molecules. Thank you very much for your interest.